Hello. Today we will start and possibly finish, I don't know, talking about uh, Fourier transforms of distributions. So, distributions arise when talking about continuous time signals. And so this is going to be a discussion that applies to the CDFT, the CCFT, and also sort of by implication, because we will talk about inversion of the CDFT for distributions, it's also going to then be a discussion which will be applicable by virtue of its inverse to the DCFT, although I won't say anything about that. There's kind of more or less obvious conclusions you can make there about the sort of inverse of the DCFT. Okay, so to motivate things, let's start with the CCFT. Okay. All right, so how should if we just take it, and I'm going to be vague about what distribution means here. You can think of it as being something in D prime, but as we're going to see today, there's all kinds of spaces of distributions whose Fourier transforms we're going to talk about. So we're only sort of speaking vaguely here. So what is sort of a natural condition? So to define FCC of theta, as a distribution again, and again of some sort. We need to indicate CC of theta behaves on test functions. Okay, so again, I'm not going to be specific about where phi lives. Okay, so in other words, what I'm saying to you is I need to make sense of this thing, all right? All right, good. So how we will initiate this is, let's consider the case where theta is theta f for f in 1. Okay, so then what are we doing? So then we're looking at this thing. Okay, and that is integral over R f cc of f of nu phi of nu d nu. Okay. Okay, to understand this, we'll use what's called the Fourier reciprocity relation. Okay. And the way Fourier reciprocity works is if f and g are in L1, and also if their CCFTs are in L1, okay, then there's a formula that holds, and it just holds by a simple application of Fubini's theorem. Okay, and the formula is this. It's a funny formula in some sense because it relates integrals of, on the one hand, a function of time, and on the other hand, a function of frequency. Okay. Okay, but nonetheless, this is what we're going to use here. So we have test signals, and test signals are in L1, at least the ones, well, at least the ones in D. We're going to introduce another class of test signals today, which is also in L1. And let's also assume that the CCFT of F is in L1. Okay, and then, okay, so then requiring, and this is, sort of an arbitrary requirement at this point, Fourier reciprocity for theta and phi. Okay, then we have FCC of theta. So let me write it out here. Okay, so as we saw above, this is just by definition. Okay, and then by Fourier reciprocity, this is f of nu, CC of phi, d nu. I should really be writing, a different variable, just like I did up here in the Fourier reciprocity formula, since this mixes time and frequency, but never mind. Okay. So the point is now is that this is, of course, just theta. And so here I have theta f. Okay. Sorry, I forgot that's theta f there. Okay. And so this is theta f acting on the CCFT of phi. Okay. And so And so what we're going to do to define the CCFT of a distribution is we're going to, so therefore we're going to define CCFT of theta by requiring that a formula like this holds. Okay. All right, good. Now, so this formula presents us immediately with some problems. Okay, so so the space in which theta lives is, defined by the space in which its test signals live. And so over here, I need to ensure not that phi match up with theta as an appropriate test signal, but that the CCFT of phi match up with theta as an appropriate test signal. So in other words, if theta is in D, then I need to make sure that that thing is in D prime, okay? And so if notice that if phi is in D prime, then its inverse Fourier transform is, sorry, if this thing is in D prime, then its inverse Fourier transform is perfectly well defined. Okay, so in other words, it's certainly true that phi is equal to FCC inverse FCC of phi. And here the inverse is just defined by the Fourier integral, okay, because this is a situation where because this thing is in D, it has all of the conditions for uniform convergence of the Fourier integral. Okay, so I can apply this, and it's just the Fourier integral, right? So this formula certainly holds and gives me the relationship between phi and the CCFT of phi. However, it does not mean that if the CCFT of phi is in D, then phi will also be in D, or the other way around. If phi is in D, then this may not be in D. Okay. Okay, or if CCFT of phi, these are really equivalent statements because the inverse CCFT and the CCFT in this case for things in D, they're really kind of the same formula with just that minus sign in the integral that changes. Okay, so if this is in D, then phi D. In fact, it will almost never be in D. Okay. All right. So there's a difficulty that arises there. Okay, and you have to think about how you might overcome that difficulty. So we will overcome this in two different ways. So they're not two ways of doing the same thing. They're two different ways of addressing this issue. Okay, they're different theories of the Fourier transform. Okay, so one way is to directly address the problem here, and that is figure out what the CCFT of something in D is. Okay, or conversely, figure out the things whose CCFTs lie in D. Okay, that's one way of addressing things. And the other way is change the space of test signals to be a space that is invariant under the CCFT. Okay, so in other words, if you take a test signal in this space that we haven't yet described, then the CCFT is in that same space. Okay. All right, so this is going to require us to introduce two new classes of distributions. What we will do here is we will introduce a class of distributions that are called ultra distributions, and these are just exactly the distributions whose test signals are the CCFTs of things in D. Okay, so it turns out that you can give a reasonably explicit description of such test signals. And so the description of those is quite a lot different from the normal descriptions of test signals that we've considered so far. Okay. And then what we'll do here is we'll introduce the class of what's called tempered distributions. So, so these will be things which include the normal test signals in D as a special case, but enlarges the class of test signals in such a way that when you take the CCFT of them, you get something back in the same space. Okay. All right, so we need to talk about two classes of distributions, and we'll start with tempered distributions. Oops. Okay. All right, so tempered distributions are so let's make a definition. Oh, sorry, I'm going the opposite way here. Okay, so a function f has rapid decay. Okay. If the limit is t goes to infinity, t to the k, t equals 0 for k. Okay. All right. And so basically it means that the signal decays to 0 faster than any polynomial function of time. Okay. All right. Okay, so then a test signal of rapid decay okay, is phi. And so, we're just talking about distributions here, so we don't need C here. right? So test signals should have two properties. One is that they're infinitely differentiable. Okay, and the reasons for infinite differentiability are exactly the same reasons as we had for infinite differentiability of things in D, and that is that it allows for a theory where all distributions are integrable in this new theory. Okay, and the other thing, the other property is that all the derivatives are rapid decay. Okay. All right, so there's, lots of properties of these things that are more or less routine. There's a prototypical example. And that is the Gaussian. Okay, so the Gaussian is infinitely differentiable and it decays to zero faster than any polynomial. Okay. Now, so this is our new class of test signals. Now, how do we define convergence? All right, so we're distributions have a continuity properties always, and so when we talked about D, we had a notion of convergence in D, which we use to define convergence in the space of distributions. Okay, so and that gave us our notions of continuity. Right, so we need to give a topology basically to this space. Okay, and this space is S of our space of test signals of rapid decay. Okay. All right, so this is as opposed to D, which we've had before. Okay, so this is a new class of test signals. Convergence in S. Okay, so a sequence. J in S converges to zero if for any pair of non-negative integers, k and r, okay, the limit as j goes to infinity, t to the k, phi r, j, t, so sorry, limit as j goes to infinity of soup of this over all t's in R goes to zero. Okay, so this is really just, of course, the infinity norm of the function t goes to t to the k r t. Okay, and so the infinity norm of these things has to go to zero, and so this is a uniform convergence requirement, right? So I'm asking for convergence to zero in the infinity norm. Okay, all right. Okay. um, so also phi j converges to phi if, of course, phi j minus phi converges to 0. Okay, so that's our notion of a topology, and we define it by convergence. And it, you have to make sure that this all makes sense. All right. Okay. So notice that D is contained in S. Okay, so this is obvious simply because everything in here has compact support and is infinitely differentiable, and so it, certainly decays at infinity faster than any polynomial because it's identically 0 outside some compact interval. Okay, so you have the inclusion like this, and if J is a sequence in D converging to 0, then, so I should be clear here, converging to 0 in the topology of D, then the sequence also converges to 0 in the topology of S. Again, this is an obvious statement. And so this just gives uniform convergence to 0 in the infinity norm. And that's certainly also true of convergence to 0 in D. But D has this other additional property that the members of the sequence, sort of convergence of the signal and all of its derivatives, okay? And so that also, okay, so let me slow down and say that carefully. All right, so if this thing converges to 0 in D, then all of these signals, I'm sorry, okay, all of these signals have compact support, and so therefore to do all of their derivatives, and all of the derivatives converge to 0 uniformly. Okay, and so that means that these things will also converge to 0 uniformly. The t to the k's will not affect that because of compact support of these things. Okay, so a sequence that converges to 0 in D also converges to 0 in S. Okay, and so the point of this is the inclusion of D in S is continuous. Okay, good. All right. All right, so a linear map theta from S into any vector space, but let's go with F converges 0. Sorry, apologies, is continuous if this sequence of numbers, theta of phi j, it's the same definition as for D. Okay, so if this thing converges to 0 as a sequence of numbers, for every sequence j converging to 0 in S. Okay, and there's lots of fun and interesting things that you can prove. So for example, you can prove that it suffices here to choose the sequence phi j to be D, okay, according to our previous recollection that D is a subset of S. And moreover, you can also restrict yourself to continuity in D. So in other words, the sequence phi j need only converge in D. Okay. Right, and this sort of has to do with the fact that this space is not just continuously included in here, but it's actually dense. Okay. All right. So much to say here, not very much of which I will actually say. Okay, so then a tempered distribution is a continuous linear map. Like so. All right. So examples. So let's think about the natural class of functions which can be represented by tempered distributions, okay? For distributions for D and D prime, denote, of course, by S prime, the set of tempered distributions. Okay. And so when we talked about D prime, okay, we decided that kind of the natural class of regular signals that we would regard as elements of D prime were the things which were locally integrable, okay? So what will be the natural class of regular signals that we can regard as tempered distributions? Well, let's let F be a signal And I'll say that it has this property of having slow growth. Okay, so what this means is, and so that's why sometimes tempered distributions are called distributions with slow growth. Okay, so anyway, slow growth means this. Okay, so it means that t squared so that some and so what it really means is that the growth of f is bounded by some polynomial. Okay, and here the degree of the polynomial is 2n. Okay, but it can, if as long as you're bounded by some degree in t, a function of some degree in t, then you're of slow growth. Okay, so then we can define theta f in S prime by theta f phi is integral t t for all phis in S. Okay, so roughly speaking, so you should do some estimates and stuff here, but roughly speaking, the reason that this integral and so this thing should be measurable, I guess. Right. And so roughly speaking, the reason that this integral exists is that phi has rapid decay, meaning that it decays faster than any polynomial, and f has a growth, which is at most polynomial. All right. So when you take the product of them, that's going to still be something that decays to 0 faster than any polynomial at infinity. All right. Okay, so that's the natural class of signals that you can talk about when you talk about tempered distributions or distributions of slow growth. Okay. So we had the Dirac distribution. Okay. Okay, and so kind of again, the reason that this works is that the support of this thing is only defined at the support of this thing is A, the singleton A, and so the rapid decay of the test signals with the compact support of this thing ensures that delta A can be applied to any test signal of rapid decay. Okay, so I'm being very loose here, giving you the intuition of this. To prove this, what you really have to do, of course, is you just have to prove that it's continuous in this sense. So you take a sequence of test signals that converges to zero in this sense, and then show that if you take the sequence phi j of A. Okay, because this, after all, is delta A applied to the phis, then so this thing converges to zero. Okay, but you know, that sort of follows more or less obviously. Okay. All right, good. So so these are two things that are tempered distributions. So so notice that, and I'm going to write down something which is, you know, suggestive, but not, but the implication doesn't follow. So I have that D is in S. Okay, and so when you take duals, you imagine that the inclusions will reverse. Trouble with my D primes. Okay, like so. Right, so that's true, right? And you know, like I said, I just kind of argued that in a kind of flippant way by saying, you know, that duality kind of reverses inclusions. You know, that's just not a very adequate explanation at all. But the fact is, you can prove this. Okay, and so therefore, every tempered distribution is a regular distribution. Okay, there. F's in one loc for which theta F is not a tempered distribution. Okay, so I know if F is in L1 loc, then theta F is in here. Okay, but the fact is there are locally integral F's for which it's not in a set of tempered distributions. And so lots of examples. Here's one. Okay, you can take e to the t, you can take e to the minus t, because e to the minus t blows up at minus infinity. Okay. And this is a serious limitation of tempered distributions, okay? Because it prohibits tempered distributions from being generally useful when you talk about linear system theory. And so we're going to see that distributions should be a useful thing for talking about linear systems. But tempered distributions are generally not. And you know, it's just that we know that linear systems kind of inevitably involve exponential functions, and those are not tempered distributions. Okay. In fact, the reason that you want to talk about tempered distributions is simply because they have the properties that you want them to have with respect to Fourier transforms. Okay. Okay, so the first, if you take the CCFT of a test signal of rapid decay, then it will also be a test signal of rapid decay. And that's more or less obvious from all the things that we said about the CCFT. So we know that things in S have two properties. One is that they're infinitely differentiable. Okay, and the other is that all of their derivatives are signals of rapid decay. Okay, so the first property, infinite differentiability, means that when you take the CCFTs, the signal will decay to zero faster than any polynomial, so it will be of rapid decay. And moreover, the derivatives are also, of course, of rapid decay, are also infinitely differentiable. And so you're also going to get rapid decay here. Of the derivatives, okay? Then, because you have rapid decay here, then you have infinite differentiability here, okay? So it's this interplay that we kind of dwelled on when we talked about Fourier transforms of the relationships between regularity and rate of decay, okay? Those properties applied in both directions ensure that the CCFT of S is in S, okay? So therefore, the definition FCC of theta by okay, by this sort of formula which comes from Fourier reciprocity, this definition now makes sense, okay? And it's simply because if phi is a test signal of rapid decay, then so is its CCFT, okay? And so if theta is a distribution of rapid decay, then this makes sense, okay? And you have to check, the only thing you have to check here, so this will certainly give you theta as a linear map from it'll give you FCC of theta as a linear map from S into, from S into the scalar field C. You just need to check continuity, but that's going to follow immediately from the definition of continuity of theta, okay? So this gives, okay, so this gives FCC as a mapping from S prime to S prime. And moreover, this is actually a continuous linear mapping. In fact, it's an isomorphism. So it's a linear isomorphism. And it's a homeomorphism. Okay, so it and its inverse are continuous, okay? So that's one way of defining the CCFT, and that is for tempered distributions, okay? All right, so maybe let's just look at some examples. So as you expect, when f is in L1, then the distribution, the CCFT of the distribution associated with f is the distribution associated with the CCFT of f. Okay, so it just reduces to the normal CCFT if f is for integrable signals. Okay, so let's take the Dirac delta. Okay, with okay, so all right. So let's actually calculate using the definition what the CCFT of this thing is. Okay. So the CCFT of the Dirac, right? So we need to see what it is applied to a test signal phi of rapid decay. The definition is that this is delta A CC of now the definition of the Dirac is that this is FCC of phi applied to the time A, which is the integral over R phi of t e to the minus 2 pi I nu, okay, but nu now, I'm taking nu to be A, right? I'm evaluating it at A, t dt. All right. Okay, but this then, let's take a look at what this is. So this is now just a phi is a signal of rapid decay. This signal, the complex exponential, is a signal of slow growth, right? In fact, it's bounded. It and all of its derivatives actually are bounded. So certainly it has slow growth. And so this is this signal of slow growth applied to this signal of rapid decay. And so this is really then just the distribution corresponding to the function e to the minus 2 pi I a. Okay, so we used this notation before. So for, let's say, e to the alpha is a function from R into C, and it's just a function t maps to e to the 2 pi, sorry, e to the a t. Okay, and so this, sorry, alpha. Okay, so this is just the notation for the exponential function with this as its exponential coefficient. Okay. All right, so the CCFT of the Dirac is this distribution. Okay, so you know, it in particular is the distribution associated with a function. So it's a regular distribution. Okay, so sometimes one writes FCC of delta A t is e to the minus 2 pi I a t. But this is kind of bad practice generally because this is a distribution. Turns out in this case that it's a regular distribution. And so, you know, in this case, this makes sense, but, you know, really, it's really kind of better to write it like so. Oh, sorry, I forgot something here. Apologies. Okay, and so the implication of this is that the CCFT of the Dirac is theta e minus 2 pi I a. Okay. All right. Okay, so now you can go through lots of interesting examples here. Okay. Um, um, and maybe I'll just do one more. Let's let t be a positive real number, and let's consider what's called the Dirac comb. So I'm going to use the symbol, this comb-like symbol is some overall integers of the Dirac at the integer multiples of t. Okay. So if you kind of wanted to draw the graph of this thing, the way this graph is often represented is this is minus t and 2t and t and 2t. Then this is sometimes graphed like this. The idea is you represent the Dirac with this thing like so. It's suggestive, it's not precise, because of course the Dirac is not a function, so it doesn't really have a graph. But so the way you graphically represent it is something like that. Okay, so it's a t periodization of the Dirac at 0. Okay, so last time we talked about periodization, so you can think of this as being like per t of delta at 0. Okay. All right, so then, you just repeatedly, or you just apply the same, that formula, okay, and, you have linearity, okay, and, you have to check to make sure that the distribution, sort of, that it's linear with respect to this sum, which is not finite now, right? So this is an infinite sum, but it all works out. And again, the way you can see that this all works out is just to literally apply the definition. Okay. So FCC of the Dirac comb with period t is sum Z of theta e to the 2 pi I n t. Okay. All right. All right, good. Okay, so that's the CCFT now for tempered distributions. Okay, so that kind of addresses our second proposed approach. Now let's look at the first one, and that is, let's see if we can actually calculate the CCFT of a distribution. And the way that we're going to do that is by understanding what the CCFT of a test signal in D looks like. Or conversely, what is the set of things whose CCFTs are test signals in D? Because again, the inverse of CCFT and the CCFT are essentially the same thing, with just a minus sign in the Fourier integral, or the minus sign in the forward transform and no minus sign in the Fourier integral. Okay, so what we're going to get here are what are called ultra distributions. So these are funny things. All right. So the first thing we need to do is we need to define an appropriate class of test signals in exactly the same way as we did for tempered distributions, and in the same way as we did for distributions, and also the other class of distributions we've talked about are distributions with compact support and periodic distributions. And in all those cases, we talked about the various kinds of test signals. All right. So we need the test signals. And I'm not going to name these test signals. I'm just going to give the symbol for them, which is Z. Okay, so it's as I say, it's a peculiar definition. So there exists an entire function, so a function on the complex, defined on the complex plane, which is polymorphic. Okay, such that on the real axis, it agrees with phi. And so it extends phi away from the real axis, and then it has a growth property. Okay, and the growth property is defined like so. Okay, so there exist constants, alpha, positive, and ck, non-negative, for every k, positive integer or non-negative integer, such that so the growth of z to the k, a phi z, is less than or equal to ck e to the alpha times the imaginary part of z. Okay. This is true for every non-negative integer k, every z, c. Okay, so there's our collection of test signals in this case. All right. So notice then that these are certainly infinitely differentiable because they agree on the real axis with an analytic function. Okay. But the analytic, and this is kind of the crucial thing, is the analytic function away from the real axis. Okay, so this is kind of measuring the distance to the real axis, the imaginary part of z, okay, grows with some exponential rate. Okay, and the exponential rate is such that if you consider the polynomial growth of a phi, okay, so you know, multiply it by z to the k, that's going to be uniformly exponential. Okay, so the important thing here is that alpha does not depend on k; it's constant out front. Okay, and so the polynomial growth rate is kind of uniformly exponentially bounded, kind of is the way to say that. Okay, all right, so how do you define convergence in Z? Because like all of our classes of test signals, we want some kind of a topology, and so you need to say what convergence is. Okay, so a sequence phi j converges to, so this is a sequence in, of course, Z converges to 0 if all right, so we're going to require two properties. All right, so the first is that the constants here in this formula can be chosen independently of J. Okay, so there exists an alpha r greater than 0 ck. Oh, sorry, I didn't mean to say r here. Sorry, I didn't mean to say Z, I meant to say r. Okay. Okay, so again, such that this property hold independently of J. Okay, so I will save myself a bit of writing here. Sorry, let me copy that. I'll do that somehow. Oh, sorry. Don't use that feature enough to do it accurately every time. Okay, so I need a J there. Okay, good. So it's a uniformity condition. I suppose I probably might have even been able to write that out faster than I copied and pasted it. Right. Okay, so this is a little bit like the condition for convergence to 0 in D, which required that there be a single compact set which contained the supports of all the terms in the sequence. This is a condition that's a bit like that, all right? It's a uniformity condition across the members of the sequence, okay? And then the other property is that this sequence of holomorphic functions, A, J, converges uniformly to 0 on compact sets in C. Okay, so this is the normal notion of convergence of a sequence of holomorphic functions, that you converge to 0, or you converge on compact subsets uniformly. Okay, and so it's one of the significant properties of analytic functions is that with that notion of convergence, the space of analytic functions is complete. So Cauchy sequences converge. Okay, and that's a special property of analytic functions. Okay, so then you obviously have so let me just jump right to the definition of an ultradistribution as a continuous linear map. Okay, so an ultradistribution is a continuous linear map theta to f. Okay, i.e. theta is linear, and okay, the sequence theta applied to Vj, the usual sequential definition of continuity that one uses for distributions. Okay, and you use it because it makes sense and it works. Okay, but we're just going to sort of adopt it as the definition. So this converges to 0 for every sequence Vj converging to 0 in Z. Okay, so that's the usual definition of convergence. Okay. All right, so some facts. D, test signals in D are also in Z and only if they're 0. Okay, and the reason for this is a property of holomorphic functions. Okay, so we required this hold. Okay, and so it therefore holds that on the real line, this function A, this holomorphic function A, has to vanish outside a compact set. Okay, so it turns out that for if you have an analytic function on the complex plane or some open subset of the complex plane, which vanishes on a converging sequence, all right? So there's a sequence in that open set which converges to some point, and your holomorphic function vanishes at each of the points in that sequence, then the holomorphic function must be 0 on the connected component which contains that sequence, right? And so therefore, we're talking about the complex plane here. Okay, so what's the situation? So the situation is that phi has compact support. Okay, so there's going to be some interval like this, and outside of that interval, I know that phi is equal to 0. Okay, and so certainly, this big semi-infinite interval here will contain some some convergent sequence, and I know that my function a phi has to vanish at each point in that sequence, and that means that a phi must be 0 on the connected component of the real line of the complex plane, which contains that sequence, which is everywhere. Okay, so therefore, if phi is in D, then a phi must be 0. Okay. So that's the relationship between D and Z. Okay, it's kind of a dual relationship. Okay. So it turns out that this class of test signals are of rapid decay. Okay. All right, and so of course, we're going to denote by set prime set of ultra distributions. Okay, so the inclusion of the test signals like so suggests that when you take primes, you're going to reverse it, and that's true. So tempered distributions are ultra distributions. Okay, good. All right. So there are ultra distributions, however, that are not there are ultra distributions that are not tempered distributions. Okay. All right. Okay, so to define one of those is more complicated than I want to get into right here. Okay, good. Now, what is the main property of the set of ultra distributions? Okay, so of course for us, the main property is going to be connected to the Fourier transform. Okay. And so the big sort of result here is the following. Main fact about ultra distributions. Okay. And that is that the CCFT maps D into Z test signal spaces is an isomorphism. Okay, and in fact, it's a topological isomorphism. Okay, so it's a linear isomorphism whose inverse is also, which is continuous, and whose inverse is also continuous. Okay, so this is a rather non-obvious statement. Okay, and so it relies on some complex analysis, right? Which is something we haven't talked an awful lot about. So it would take us quite far astray here. Okay, so this is a deep statement, which nonetheless provides the foundation for defining the CCFT of a distribution. Okay, so thus we define CCFT from D prime into, so I need to be using C here. To Z prime by the expected formula, which comes from Fourier reciprocity. Okay, so I take FCC of theta and I apply it to, well, what I'm going to do is I'm going to apply it to, because well, let me write down the formula and then I'll say what I apply it to, because that'll make it clear. Okay. So this side will make sense if the CCFT of phi is in D, right? Because theta is in D prime. Okay, so therefore, by my assertion that this thing is a topological isomorphism, this means that phi should be in Z. Okay. Okay. Right, so that's how you calculate the Fourier transform of a distribution. Okay, you get not a distribution back, but you get an ultra distribution. All right. Okay, so there's much that you can say here, but the benefit of this is that you can now include okay. So you can take a real exponential, which you cannot calculate the CCFT of, because a real exponential is not a tempered distribution, but it is a distribution. And so when you take its CCFT, you're going to get back something, and you can calculate this. And I'm not going to sort of go through it here. If you want to look at the course notes, you can do that. And so you can calculate the CCFT of e to the AT, and what you do in doing that is you calculate actually not so much the CCFT, which is an ultra distribution, but you calculate it knowing what it as kind of a holomorphic function, and so so it's a very interesting kind of a construction where you work in the complex plane rather than on the real line, and that's not surprising given the definition of ultra distributions as being sort of dual to some set of functions which are essentially holomorphic functions on the complex plane. Okay. And so the benefit of this for talking about system theory is this allows you then to talk about applications of the Fourier transform in system theory without restriction. Okay, so you don't have to restrict yourself to talking about systems which have say impulse responses that are tempered distributions and things like this. Okay. All right, so that's nice. So I'm going to stop there for now, and next time we're going to talk about the CDFT for periodic distributions and ultra distributions. Okay. All right, and so what we're going to get out of that is some very interesting constructions involving Fourier series. So Fourier series can be made to make sense for completely arbitrary sets of coefficients by talking about periodic ultradistributions. Okay, but that's next time.